Now it's our great pleasure to introduce our keynote speaker, Professor Huimin Lin from the Chinese Academy of Science. Professor Lin received his PhD in computer science from the Institute of Software, Chinese Academy of Science, and he's currently the director of a very important laboratory in software engineering. He's also a fellow of the Chinese Academy of Science. His major research interests include concurrency, model checking, model logics, formal methods, tools, and algorithms for concurrent systems. That is also the focus of his keynote speech this morning. He's on the editorial board of a few very prestigious journals. He's also on the steering committee of a few international conferences in the related areas. So let's welcome our keynote speaker, Professor Huimin Lin.
Thank you very much. It's a great pleasure to be here. Today I will talk about how to make sure that concurrent program, compiler software system are safe. Concurrent software system is typically has a number of components running in parallel. With today's networking technology, so most systems are concurrent. And many so-called safety critical systems are concurrent software systems. Here I just list a few, like nuclear reactor control, medical treatment systems, train control systems. You may add a lot more into the list. A system is safety critical if it does not function normally as expected. Then a heavy loss of property or even human life will be incurred. So I just here to mention, remind you, accident, a train collide accident which took place in South China city of Wenzhou last year, in July 23rd, which killed 40 people and injured almost 200 people. It was once a major accident in Chinese transportation system. After that, there was a heavy, very intensive investigation into the accident, and the report was released at the end of last year. It's about half-year investigation. According to the report, the main technical cause of this accident is default in the railway signal control system software. So it's a software system, a bug which causes the accident. And more than 50 people got punished because of the accident, including the company which produced this piece of software. So it's, I saw the report, I get this detailed technical analysis results. Actually, if you use the techniques I talk today, the accidents can easily be avoided. So it's really a strategy. It's something that shouldn't happen, but it happened. The concurrent systems are important, but they are complicated. The behavior are complicated because, as we know, for concurrent system, the complexity of the system grows exponentially in the number of concurrent components. And typically, we have several dozens of components. So the complexity of the whole system is like is very high. So it's usually unmeasurable. You really need to invent some techniques to do that. So because complication, so safety properties of concurrent software system are very difficult to ensure. Now let's make comparison between concurrent program and sequential programs. A sequential program, we all familiar with that. When we're a student, we do homework. First we write sequential programs, not concurrent programs. Sequential program can be regarded as a function which maps input to output. It must be terminating. If it's non-terminating, it means there is a bug. For any given input, it must give us output. If we run forever, then there is a so-called dead loop. So it's a problem. And they are deterministic, means if we give them same input, they produce the same output. If actually it's stronger than this, not only same input, same output. If the same input, they have the same execution trace. The execution will be exactly the same. We put the input this day, today is executes. We record the execution sequence, and we put it tomorrow the same, we feed it with the same input, either we follow exactly the same computation steps. So this implies that failure is reproducible. If we do a test on sequential program, if fail some input, we get some bug, we found some problem, and we can do it the second time, and it will give the same problem. So bug location, so that is very important condition for test to be meaningful. On the other hand, concurrent programs is not something that's from input to output. It's something interactive with environment. It is a perpetual process. It's never stopped. So it's typically a concurrent program. It's non-terminating. If we look at any server program like Apache or anything, it starts with our rate, which is while true to something, which is for a never-ending loop. And on in the loop body, it will try to receive some request from some client, and they dispatch on the requirement to appropriate computation and send it back to the client what they want. So concurrent programs are non-terminating. What makes things worse is non-deterministic. Means that if we start the program with some initial condition, initial configuration, so it's not usually not a simple input data, but a configuration. And it may run and give us something, maybe something wrong, we don't like to see. But if we start them again with the same initial configuration, I mean the default behavior, the behavior, wrong behavior will not repeat again. Why is that? Because concurrent program may run in a local, if they run in the same machine, then there's a scheduler there, which in the operating system typically scheduling all these executions, relative speeds of these components of concurrent threads. So these threads, they cannot control their own execution speed. So even with the same initial configuration, because scheduling policy, they may have give different execution trace. If the system is distributed and they connect by network, it seems to get worse, because in network, anything can happen outside of the system, and so it may cause this unexpected delay or something to the program. So non-terminism is bad. It means that the failure not responsible. If we apply test to a concurrent program, we get some output. We see that something which is good, is running as expected. But there's no guarantee that if we run it the other day, it will give the same behavior. It may cause some problem. So what to do with that? Of course, there are many people nowadays still have been studying research on testing concurrent programs. And there is another approach which is called model checking. It's developed by these three guys now 30 years ago. Model checking is an automatic technique to decide, to check if a concurrent system has desired properties, desired behaviors. In model checking, first, the system is modeled as a transition system, usually finite state transition system, and the property is specified as a logical formula in some temporal logic, like CTL for computational tree logic, or LTL linear time logic, or propositional mu calculus. So these are most popular logic used in model checking. Among them, mu calculus is most expressive in the sense that both CTL and LTL can be mapped into subset of mu calculus. So if the system, the model is a finite state, then it is decidable if the model satisfies phi, which means if the system is model satisfied, it means the concurrent system has a behavior described by the formula phi. What makes model checking useful is that it decides not only just give you yes or no answer. If the answer is no, means that the system does not have the required behavior, it will generate a counterexample which typically exchange trace and is leading to the faulty state. So for model checking, false location is almost free, count free. Of course, it adds some cost because when decide the satisfiability here, if M satisfies phi, we have to search, complete search space. We have to do exhaustive search on the search space. So it's really cost. It doesn't like testing. You just give a configuration, it runs. It's actually, when do model checking, we have to explore all possible runs in some encoded way. So model checking has been there for 30 years, and most work on model checking is focused on system skeleton, which means that data aspects are largely ignored. This reflects in two facts. First, these logical uses are propositional. Propositional logic, in propositional logic, you do not have data variables, unlike a program. A program may always have data variables, but for propositional logic, they cannot talk about data variable. And in a concurrent system, different concurrent components, processes, or threads, they cooperate by exchanging messages. So, but in most research on model checking so far, this data, this message exchange between processes are most absolute way. So, message passing or message exchange are synchronized to pure synchronization on signals. So these two features made the current technique, model checking technique, is not really suitable for concurrent programs, because in concurrent programs we have data variable. Data are important. We compute on data. And in some cases, systems with serious safety bugs can get model checked because we ignore data. I will come back to this, show you an example at the end, towards the end of this talk. So in this talk, I will try to, the research has been carried out in our lab for about 10 years now, how to model check concurrent programs. We do not do this simplification. We direct operate on program data. Okay, so a talk will consider 5 parts. By first introducing symbolic transition graph as a system model for concurrent programs. And then we present a first order extension of propositional mu calculus. And I call it first order mu calculus. And of course, to model checking, we need model checking algorithm. And I present the algorithm for this logic, first order mu calculus. I'll show you some case studies, and finally we'll sum up and point out some future research directions. So the first, our system model, which was called the symbolic transition graphs, in contrast to the concrete transition system, because symbolic in the sense that we have data variables. Data variables, just like a program written in a program, it does not have value associated. So each node in the graph is just a directed graph. Each node has associated set of free variables. And edges connecting two nodes carry three pieces of information. B is a Boolean condition, which means that if B is true, then this transition can take place. If B is false, then this transition does not take place. Where X become E is just a multiple assignment. Alpha is a computation action. It could be an input action or output action. So on channel X, on channel C, on the channel. And tau is we use this invisible action to denote internal communication. And there are some considering constraints. So here is a very simple example. We have stack of capacity 2, so you can push it. So if you omit the condition, which means the Boolean is true. Yeah, if the assignment is not there, we also don't write it. So you can push your do a push out start from empty stack. We push it, we get then we arrive at the node which has free variable X. Here we have two choices. We can either pop it up, pop the elements, pop the stack and go back there, or we can push another thing like Y into the stack, and then we do back. Here is a counting machine, which is a very simple example. From initial load, we can input something, we will start input something number in X. If X is positive larger than 0, we count down by decreasing X until X become either 0 or minus, then go, the counting finish. Here is another example which is a real example, very simple. It's a part of a conference protocol that we do that in our case study. So first, the conference system is idle. After we started it in a state, here we call record X. In record X, you can either do an input or do an output. Yeah, for output end, then finish. Do nothing, the conference is over. Or it's input, if the X is not than 0, you can input it again. It's actually like that. So this is just like very familiar to our what's called flowchart programs. And the difference are that there is low condition loads. In flowchart, we have some diamond loads, typically, which to decide if X larger 0 or not. Not kind of yes, now you have yes, age outgoing or low outgoing. But where here, these conditions, or we call guards, the B, the Boolean condition, are carried on edges. And the different edges out of the same node may have their guards true at the same time. So this is kind of a source of non-determinism. If they are both two outgoing edges with the condition the guards true, then one of them may be chosen randomly to execute. And two symbolic transition graphs can be composed parallelly with some restriction on channels. So G, given two graphs, symbolic graphs, G and H, their parallel composition is just a product of these two graphs. Here, so because product graph, each node is a pair of nodes come from G and H respectively. And so if one for the N, which is G, if G has H out of this out of it, then this the node in the product graph have a same out edge. Of course, we have to meet these we have to take care of the variables which are in the other graph. So nothing happened to the variables in the other graph. Similarly, if M, so graph H at the node M has outgoing edge, the product graph also have the same edge to the next node. For if M and this pair has input edge and output edge, and they match on the channel, then communication takes place. And we produce an invisible action tau for internal communication. And here, this expression E will be updated by substitution sigma 2 and assigned to the input variable X on the graph G. So communication here is just inter-process assignment. So from now, this system, the symbolic tensor graph has the variables, data expressions. So from a symbolic tensor graph, we can induce a standard label transition system as people used in for model checking. Basically, we instantiate variables, give variable values. So a state of the label transition system is a pair. First, M is a node of the graph, and rho is mapping, is an environment which is mapping data variable values. They provide the data variable values. So thus gives this state we call the state of label transition system induced from STG, from symbolic graph. So the transitions are very simple. If the node M in graph G has an outgoing edge, I don't call it a transition, it's an edge, because transition may not happen. So, and the current environment, within the current environment, B is true, so rho satisfies, so B evaluates true under the rho, then there is a transition can take place, the same transition here, and the system move to the next node with this environment updated by an assignment. It's just assignment. So we evaluate E in the current environment rho assigned to X. So for output, similarly, but we have to evaluate these. First we have to substitute X in E prime, so update the E prime by this assignment, because assignment that must do before the output. So we update E prime and then evaluate. For input, similarly, the difference is that we leave this input action is there. The variable or input variable is there. And so I talk this later, for later use. Okay, so we have the system model. We know how to system model to give our system model, which is symbolic transition graph, how to induce a label transition system. So we need to come to the logic, the property specification language. So I talk, as I said, is a first order extension of Parisian mu calculus. So the syntax is simple. Here we have Parisian variable P, conjunction, disjunction, and because first, so that is in Parisian mu calculus, and Parisian mu calculus we do not have quantifier. It's propositional. We have two modalities: diamond modality and a boxed modality. For propositional mu calculus, alpha is just axiom, nothing, because it's just A or B. But in our case, it's first order. Alpha could be an input, could be an output. So alpha itself involved variables, input variables, and output expression E may have some variable there as well. So, more importantly, because we have first order logic, we have first order quantifiers for all x and is x. Semantics. A formula is interpreted over a label transition system, which is induced from our symbolic transition graph. So we say that a load, remember a load in the transition system is a pair, a state. A state of a transition system is a pair, consider a load in a symbolic graph and the environment rho. Provide values for free data variables. So in the state, this state satisfies this formula if there exists a state, another state, such that from the current state we can do the transition as required here, do an input transition, output transition, and reach another state, and rho prime. And the residual state satisfies the rest of the formula. So diamond is just something like says that there exists a transition in the label transition system which can do this action, output action. For box, instead of exists a next state, it requires for all states such that can be reached from this state by doing this action. The residual states must all satisfy phi. So box is something like a reversal quantification over branches in a graph. And for input, diamond input, which there exists one, remember that for diamond, for input in our transition system induced from a symbolic graph, we have y here. Yeah? We have y still there. So if it can do a transition, input transition, and if we substitute x and y with the same value, we substitute y with v, here we substitute x with the same value, the residual state satisfies this substituted phi. So we require that after input transition, the input variable must be instantiated to all possible values. They still satisfy the rest of the formula. And similarly needs to be for all. This would be box. Made mistake. For box, it's just all residual, all input transitions. They must be rest are the same. So we look at this logic, which is finite. There's a fixed point, low recursion here. So it's only finite part of the first order mu calculus. It's finite, so its expression, it can express some interesting property, but not very powerful. For instance, we can say that a process will eventually send M along channel C, vector M along channel C, within three steps of computation. And we write this down, this formula in our logic. It says that it should have a transition which output vector M along channel C. If in the current state it can do the output, it's fine. So it's true, because they are disjunctions. If we cannot do that, then after here is a hyphen, which is a wildcard, which matches any action. Or after any action, it can output this. So after action means after a step of computation. So in the second, if in the second step of computation, it can output, then it's also fine. Or in the third step of computation, it can output. Yeah, so it's fine. So we can write like this. However, we cannot say that this process will eventually send M along channel C. Eventually means after arbitrary number of computation, arbitrary number of steps of computation. This cannot see, cannot write in our finite logic. So to do this, we need fixed point formulas. Now, so this familiar approach to describe infinite behavior, like in propositional mu calculus, is to use least fixed point. With mu for least j, such that it can output either it can output can do the output m on channel C. That's fine. Or if we cannot, then after any step, after one step computation, we come back here because it's fixed point, so it can be unwinded. So it's after. So first, if this is true, it's fine. It's not true, we unwind it. Unwind once, then unwinding means that we substitute j with this sub-formula here. So we substitute j. So the first disjunct is output, and the second is this thing. So if after one step of computation it can output, it's fine. Or if not, we unwind again. So so there's x here should be j. We unwind it. We replace j by this sub-formula again. So so after one step, two step, if we can do output, that's fine. Otherwise, we unwind it again. So this is an infinite disjunction. It's true only if one of them, of the disjunctions, is true. Yeah, so it's anyone, could be anyone. So it could be after any number of computations. So that's fixed point. So can we just use this this construction for our purpose? There is a danger, because first order mu calculus is different. We have quantifiers. What makes logic first order logic different from propositional logic? In first order, we have data variable, and we have quantifier over data variable. So we consider this logic, this formula A, which defined as there exists x such that, so z we use provisional variable. So exactly as we were saying, but the difference we add is this essential quantifier here again. There are two essential quantifiers, so they have different scope. So, so this is formula. So we know that quantifier can be renamed in first order logic. So if we rename x to y, then this should be equivalent to this formula. B should be equivalent to A. However, if we unwind it, because fixed point means can be unwind in arbitrary number of times, we just unwind it once, then we get, for A, we get this thing, and here Z is substituted by the whole, this sub-formula, which is like that. Yeah. So this should be, that is xz, I omitted it. And we unwind B similarly, then we get these two formula. They are not equivalent. To see, it's easy to see that because this x bounded by this essential quantifier, however, this x now is bound by this quantifier. So the second is x. So the scope of x for this x, the scope is just there. For this x, the scope is here. There are two different x. For B, after unwinding, we get this formula. Here, this x was bound here, so the scope is there. Now, because unwinded, x is a substitute appear here. Now, this x is not under scope of y. Instead, it's bound here. So these two x actually must be the same. While in A, these two x are different. So which means that it's a quite subtle thing. Means that straightforward introducing a fixed point into first order mu calculus is dangerous. And the problem is that because Z is is a proportional variable. It takes low parameters. And however, because a fixed point means it can be unwinded. It means x, actually z, actually stand for the whole formula, for this sub-formula, the body of the fixed point formula. And here we have x free. So z potentially has a free variable x. Similarly here, z have x free. But the syntax is inadequate. It's not adequate to express this fact because it's a proportional variable. It doesn't take any parameter. Okay, so I explained that was a problem. So the syntax is not adequate. So our solution is to use what we call predicate variable to form fixed point formula. A predicate, as we know from first order logic, a predicate is a function from data. Syntactically, is a function from data expression to propositions. So data expression here actually is a parameter to predict to the function. So we introduce a list of predicate variables. Each has an arity, indicate the number of parameters it can take. So now, for this finite part, we add this fixed point operator, which are functions. It's lambda. Lambda could be just a predicate variable or fixed point, least fixed point formula or greatest fixed point formula. And give any formula, we access the free variable x here, so this is a function. So lambda are functions. And to form a formula, we apply the function to parameters, actual parameters. So this x here can be seen as what we call formal parameter of the function. And this e here is actual parameter of the function, just like in procedure call. Now it's scoping, yeah, as usual. Now we can read the formula A, which we see before, in a more cumbersome form, which explicitly we use a predicate variable with one arity 1, which can take one parameter. So it can apply to this x, form a proposition, and we abstract away here x, and we apply it to the same, I mean, it could be e could be anything, so we just use x. Now we can change, remember that b was, in the previous slides, was obtained from a by change this boundary variable here, x to y. So we change x to y. Now if we change this x to y, because now this x is in the scope of this quantifier, so we have to change this x to y as well. And then there's no problem to see that these two formulas are actually equivalent. So there's no difference. Okay, so I don't know how many people are familiar with fixed point. I give some intuitive some explanation of fixed point operator. So let's start look at the least fixed point. We use the counting machine as an example. So it says that this formula says that after input start the counting machine, it can either immediately finish, so go up to a go, or it can do a down and then back to Z and back to here. So it means that, so here is once the first initial configuration, so you can start and then get in here. So this means is the, because least fixed point, it says that after finite number of these done, this goal should take place. So this fixed point intuitively is for finite looping, just like we write a while program, a loop program in our sequential program. It's loop, but it has to stop. So it's finite. It cannot loop forever. So if our logic allows infinite length or formula, we actually can understand it that way. So least fixed point formula can be understood as we start with force and unwind it by substitute phi I, substitute j with phi I in the body of the recursion of the fixed point formula. So at countability number times. So it's an infinite formula. Unfortunately, it's not part of our logic. Our logic is finite. But we can use this finite expression to denote, to represent this infinite disjunction. So that's least fixed point. It means that this is true if and only if one of these disjunct, one component subformula is true. And it once must be true, so it's a finite looping. Because each is like a loop, is unwinding. So after finite number of unwinding, it should stop. Now for grid fixed point, we use the stack example we see before. This formula says that we can push x to a push. And then this said that if we ask if after x is pushed, we immediately pop it. So that's the formula mean. And we want to say that this behavior can be there forever. If it push, pop, push, pop, push, pop. So this formula actually means that you have to do push, pop forever, which means new grid fixed point for looping, but for infinite looping, never stop. Intuitively, the same game can play here. We start with phi 0, which is true. Every time we unwind the formula, then the j, least grid fixed point formula actually is equivalent to this infinite length formula. So every conjunct must be true. So it's an infinite computation. So when I start semantic program languages, that would be 70s, 80s, and we read the book. The while loop was meaning what while loop was given by least fixed point, and no textbook on computer science ever mentioned least fixed point. Because at that time in the 70s, we do not come to understand infinite computation, like a concurrent program. We are mainly interested in sequential program like Fortune, Argo 60, and they are all has to be to stop somewhere. So only least fixed point is useful. But now with concurrent computation, infinite computation are important. So you have to use it as well. So formally, mu x lambda is the least solution of the equation x equal lambda. So x equal lambda is an equation. It may have several. It may have no solution or may have many solutions. But for our logic, because our logic is positive, we don't see negation there. So it's positive, it's monotonic. Monotonic guarantees the existence of solution. So the solution of x equal lambda is always guaranteed. Now the equation may have several solutions. So the least solution is this form, is the least fixed point. So this, as we said in previous slides, This 3-point formula is good for describe terminating computation for sequential program, which is a feature of sequential programs. Now for nu x lambda is a great solution of this same equation. So it's a grid of x lambda, nu x lambda is a grid fixed point of x. So it corresponds to non-terminating computation, which is a feature of concurrent programs. So actually, this notation is quite confusing because according to this, our interpretation, it's better to use to write mu x dot x equal lambda or nu x equal lambda, which means that the nu x takes this solution as this equation, and nu x takes this solution of this equation. However, logicians, because this logic was first started by logicians of computer science, they said that this x here is somehow redundant. And they like concise, so it makes things difficult to understand. Anyway, so fixed point can be mixed. For instance, this formula says it's always the case that whenever a value is received via channel R here, it will eventually be sent along channel S. So this is the least fixed point formula. So this X, after received, it must be sent along channel S. See, in finite many steps, eventually it will be sent. Now, the outermost, we have least fixed point, means that whenever, forever, a value is received, it must be sent in finite many steps. So I have to, anyway, here, because arbitrary listing of least and the least fixed point affect complexity of the model algorithm, I will skip the last part because we are interested in a safety property which is simple. So probably I will skip this argument as well because it takes time to explain. Basically, the algorithm, I mean, because we have these alternate depths, we use stack, we employ a stack. We call multi-stack, which is array of stacks indexed by alternate depths. Each stack has a local top, and the whole array of stack has a global top element. We also map most. So push something into a state into a stack means you push the state stack into his depths, correspond to his depths. But pop means we pop it from the global stack, the global top of the stack. So anyway, I'm not. Actually, the algorithm follows the semantics very closely. If you have box operator, you have to look all possible residuals. And for diamond, we just emphasize once enough. Okay, so I did that. One feature of the algorithm is that for input variable, we do not instantiate during here. Instead, we instantiate on the fly. So when we check this input X, the process, the transition system against this formula, suppose X, Y arrange have 10 in this area, in this range. If we instantiate it before the algorithm, then both we instantiate into 10 different conjunction or choice, which result in 100 comparisons during the execution time. But if we do it on the fly, each time when we compare the two, we pick from one from them, instantiate both of them, and two. So we only need 10 comparisons, so it's more efficient. That's more thing. Now for safety property we talk about today, it's sufficient to use alternation-free fragments, a subset of the logic. For alternation-free mu calculus, the time complexity of this algorithm I showed before is linear in the size of formula, so it's very efficient, just like in CTL. Now, as I promised, we did some case studies. One is the Gorman 2004, which is a cache coherent protocol. It has some, I have no time to explain the protocol. Many people may be familiar with that. we have to do abbreviation. Always phi is a fixed point, a grid fixed point formula. Phi, so phi means phi should remain true over any computation, any step computation. Now, for cache coherent protocol, we introduce two things. One is cache consistency, which means control consistency, which means that no two clients can have different clients can have the exclusive hold of their cache line. Yeah? So it's and there's another important requirement for data consistency, which means that whenever memory consistency means whenever directory is in exclusive mode, then the memory should be fresh, should be the data stored in the memory should be the latest one which assigned to the memory. And also we have cache consistency. Means any client, if the state is not invalid, his data must be fresh. This is the newest. So when we start work, this program has been shown to be correct by two groups at least. We read the paper, and they saw that they more check it in their model. However, when we do it, when we try to model check it against these two properties, only the control consistency probably goes through. But data consistency fail. So it means that the protocol doesn't satisfy data consistency. So we are quite nervous because we thought that maybe our algorithm is buggy. And then we read the paper again more carefully. One of the paper actually complete integral data path, and the other they have data path, but they only restrict the data domain size to 1. So data only had 1 element there. So and in our experience, we set data domain size to 2, and we found a bug. And we analyzed the counterexample generated by our model checker. The problem was easy to fix because. And our question is that we know that this model, this protocol is correct for data domain size 1 and 2. Now, how about data domain size 3 or 4? We are not sure. So what can we do? We cannot emulate all possible data size. Yeah, 3, 4, 5 is forever. But we noticed that the data in the cache coherent protocol, that the top protocol does not examine the value of the data. It just put there and then take it out somewhere. So this we call data independence. So for data independence data domain, we have better also like data communication protocols. And they don't examine the contents. Either the data could be a video or text or voice. It doesn't matter. The protocol itself does not concern about this data. So this data expense, can they collapse into a single just one? Because it doesn't matter if it's not. Here is an example. I just showed a very simple example. If we the process can do 2 input and then output X, output Y in order. If the formula like that, input X, input Y, but output Y first and output X next. So does it satisfy? Apparently, it is not. Yeah. However, if we restrict data domain to has only 1 element, this is true. It's satisfied because they cannot distinguish between X and Y. They both have the same data value. So we have some algorithm we can handle this data independent case, which is not very complicated, but I do not go any detail. It's easy. It just use some schematic values. This technique was developed by in 70s by people do optimization of compiler. They do data flow analysis using the kind of technique. So for this protocol, we set the data type, domain type to data independent, and they got more check it, which means that this protocol is correct for any size of data domain. Of course, in a verification, we also use other abstraction technique. like parameter expression, by simulation expression, which are very effective. Without this expression, I mean, we just carry out in a simple PC with the Linux with 4 gigabytes memory. Without this operation, we cannot do it because the state is blown up. And we do other case studies, such as conference protocol, with more flash conference protocol was the famous one. It's very, very complicated, and we have to use much more operation technique, like environment operation, cross-clustering, parameter truncating. These are domain-specific. Environment actually is more or less more general technique. Okay, so I'll sum it up. We talk about these things, about the system model, symbolic graph, and the first order mu calculus for property specification, and then we have algorithm for model checking. And we have a case study show that data accuracy is important. If you ignore it, you may get something wrong. The future, current direction actually, of course, new action techniques is vital for model checking work. Model checking has suffered problem of state explosion. And the best way is to address, particularly some domain-specific application in our own experience. They are powerful, they are domain-specific, so they can abstract a lot more. Also, so far, one criticism about particularly people doing testing said, you do more checking, but you do not work on the code, you work on the model. So, of course, we defend that you do model-based development, you have model before you have code. So, anyway, so it's two different communities, they just argue together with each other. But I just say that some people in model checking actually look at this problem. We want to direct work on code. One's technique which is called bounded model checking, which we create models from source code. Yeah. But the one problem, serious problem we are encountering here in this, when I'm doing this, is library function calls. Because any program, meaningful program call library function. But library function, we do not have source code available. So we are working around on this, find some techniques to work around on that. And also several people, many people working on how to combine model checking with testing. Basically, my software do that. I mean, a lot big company they do that. Basically, they try to. It's a combination of model checking and testing. It's still a kind of testing. They call model checking, but it's still kind of testing because they do not check property. Instead, they try to use model technique to explore. Instead of testing, you just every time you give input, start the test, you just give one execution trace. But they try to instrument in the code so that you can explore more traces, which is to make it effective to find bug. Because in the industry, so model checking actually is not used as a verifier, more used as a bug hunter. Like in Microsoft, they have group people, many people working on model checking. They use their model checker, just run it and try to find bug. And so far, model checking basically is a yes-no technique. Yeah? Of course, when you slow, it can give you a counterexample, which is useful. However, in many practical systems, if you really look into find infinite system, you cannot explore exhaustively all state space because it's infinite. One thing to design is to come up with some technique which, instead of search all possible states, we just search part of states. And instead of yes, no, we give some likelihood. But this is difficult, very difficult one, because first we need to define, to come up with a temporal logic, which allow us to do that. So it's a part of the current work we are doing. I will stop here, so I will run over time. Thank you for your attention.
Do we have any questions? Yeah, please use the microphone we provided.
Unless you're doing model-driven engineering, you're unlikely, you're starting a program from scratch using best practices in model-driven engineering, you're unlikely to have a model for your source code. And I was wondering, since you mentioned it as a future research direction, can you give us some insight as to where we're at in generating models from legacy source code repositories that are fairly large, on the order of operating systems like 1 million, 2 million lines of code? That probably can't be done now, I guess.
Yeah, sure, yes. Okay. I mean, this you have 1 million line of code. Actually, there are several papers on that report from Microsoft, a lot. What they do, of course, they do not. This successful story are most are concentrated on particular property, which makes successful. For instance, in Microsoft, I think it's Godfrey, which is Microsoft actually in Redmond. He did a model check is just for check buffer overflow, which Microsoft worry a lot. He look at this code, he write this, and he absolutely all this code, part of the code, with nothing to do with buffer overflow. So he's interested in the memory location and array indexing, that kind of thing. So actually, it's very successful. I mean, it's just.
I have a question for you. Do you think it's easily to extend extended model checking to analyze a binary execution at runtime? Do you think it's easy, or it's gonna what's gonna be the main difficulty to do that?
You want to do that on a runtime? Actually, this approach is very similar to that. It's close to that goal. We have a colleague working on that. Boundary models, basically, you take the source code. It could be a model, could be a source code, doesn't matter. Bounding means that you set a bound on the execution depths, 1, 2, 3, 4, 5, and then you, for some like CTL or temporal logic, you modify logic a bit, add something so that is whenever after a finite number of steps, because you set a bound on the depths of your exploration, state exploration is always stopped. You can always stop because it's finite steps. So you try, you set a k, so you try, say start with 3. You try case 1, so 1 step unfolding, and there's 2 steps unfolding, 3 steps unfolding, and you stop. If you find a bug, then it's fine. So it's basically bug hunting. If you do not find any bug, you stop. You cannot say that the code is bug-free. So, so this is still is not. You mentioned about runtime replication. No, it's not runtime. We're still working on the before the code run, but it actually run the code. So run the code before the code put in employed.